cornerstone of AI for 25 years. Yet in the end, creating all these matching connections took up too much time. It was also difficult for these machines to match all the different patterns without running into a combinatorial explosion. The philosopher John Searle pointed out that you can think of artificial intelligence in two different ways. There's strong AI and weak AI. Strong AI is when you have a machine that displays all the behavior that you'd expect from a full-fledged artificial person. This is usually what you see in science fiction movies. These are artificial beings that have emotions, a sense of purpose, and can even tell jokes. Some computer scientists also refer to strong AI as general artificial intelligence. General AI is a broad intelligence that doesn't just apply to one narrow task. Think of it this way: a strong AI machine might learn a new language just for the joy of learning a new language. On the flip side, patterns that the expert created to reach a possible diagnosis. In the end, expert systems run into the same problems as any other symbolic system approach. They would lead to combinatorial explosions. There are simply too many symbols and too many matching patterns. There's too much information serving as input. Think about all the different questions a good doctor might ask to reach an accurate diagnosis. Yet the symbolic system approach was a key starting point for artificial intelligence. It's still used to this day. In fact, many experts still refer to it as GOFAM, or artificial intelligence used something called the symbolic systems approach. This approach allowed machines to act in a way that seemed intelligent, but in reality, it was just complex pattern matching. The symbolic systems approach allowed early programmers to create expert systems. These machines could do things that were normally left to experts. They could diagnose illnesses, give you a credit score, and even help you with your taxes. The problem with these systems is that they created long lists of matching patterns. They also required experts to create these patterns. You needed someone who knew Chinese to match every possible phrase. Maybe it'd be the doctor who would come up with an answer to every one of a patient's questions. They had to create these long lists of matching patterns. Sometimes this is called combinatorial explosion. This type of effort made it extremely difficult to create robust expert systems. There was also the very real possibility that you wouldn't find a match. So a nurse might go through a dozen questions and only at the end find out that there's no match. Or a Chinese speaker might
Write a statement that was not included in any of the long list of responses. These challenges made it really difficult for expert systems. Because of that, they started to disappear in the late 1980s. Still, the disappearance of expert systems didn't entirely eliminate the symbolic systems approach. Instead, you can still commonly find this approach in what's called planning artificial intelligence. It's called planning artificial intelligence because you still have to plan out how to match your symbols and patterns. It tries to solve the problem of the long lists that you get with the expert systems. Instead, it uses something called heuristic reasoning. This reasoning gives artificial intelligence a form of common sense. It tries to limit what patterns the program has to match at any one time. This is sometimes called limiting the search space. Think about how heuristic reasoning might work for the Chinese. Then you might use heuristic reasoning to limit the possibilities of the first note. So the program might expect something like hello or how are you? Maybe even something like do you speak Chinese? If the program is expecting these as a first note, then it limits how far it has to search to match the pattern. One common place that you'll see AI planning is with navigation systems like Google Maps. Here you'll put in your starting location and your destination, and then the system will step through all the possibilities to find you the best route. It's still using a symbolic systems approach. All the roads and street names have been carefully mapped out. The system matches your destination with the patterns that it has in its list. You may have even seen one of the Google mapping cars driving on the road, collecting the street names of all the best routes. These Google cars were creating their own lists. If you turn right at the stop sign, then you want to turn left when you reach the end of the road. The big difference is that a planning AI system like Google Maps uses this heuristic reasoning. So Google Maps knows that there are only a few possibilities each time you make a turn. You won't be able to turn right onto a street that's hundreds of miles away. Even though it's considered old-fashioned AI, the symbolic systems approach and planning AI are still used in many new projects. Planning AI performs really well in systems that have predefined symbols and patterns. You can see this with driving directions, but it also works well with legal contracts, logistics, and even video games. The trick is to make sure that your heuristic reasoning is accurate. Like most common sense, if you turn out to be wrong, then pretty much everything you assume afterwards will also be incorrect. Think about how your mapping software might react if early on you turn onto a road that hasn't been added to its lists. Even though you might use your mapping software every day, it still comes from symbolic system ideas that came out in the 1950s. So a lot of newer AI projects just assume that they should use newer approaches. The newer approaches might not be the best fit for your organization. If you have a new AI project, don't be quick to dismiss the benefits of good old-fashioned AI. Symbolic reasoning and planning AI worked great for machines whose matching patterns were limited. You could easily use this approach for creating a program to help you with your taxes. The IRS only has a limited number of rules, and you can go through the paperwork step by step. You could even create many if-then statements. If you have a dependent, then fill out X form. If you live in this state, then fill out the Z form. The challenge with this approach is that if the list of possibilities gets too long, then the system is difficult to manage. Let's say you wanted to create an AI program that identified animals from a database of images. You wouldn't want to create a list of these matching patterns. That would have too many variables. Imagine all the different lists of size, eye shapes, number of legs, or other distinguishing features. You also wouldn't want to create something like, if it has fur, then check to see if it has whiskers. If it has whiskers, then check the shape of its ears. A list like this would become way too long if you wanted to match many different kinds of animals. There are also way too many opportunities where the system could get stuck. Maybe you couldn't see the whiskers in a low-resolution photograph. Then you have an unidentified image. That's why early AI researchers started to wonder if instead of planning out matching patterns, a computer could be programmed to learn the new patterns by itself. They called this idea